chemistry via coating. If we can achieve that, we can solve the problems due to the different surface properties of the particles, which means it doesn't matter what they look like at the initial stage. For example, some particles hydrophobic, some particles hydrophilic, some particles like amorphous, some particles surface like crystalline. But it doesn't matter because we just put the same powerful shoot on them, which is the coating. They not just look like the same, but perform the same. Okay, this is the trick. So in order to prove that, we examine the different drugs to prove that. We use the same material. So this is another drug for inhalation. We micronize them, and we can see the particle shape is different from the salbutamol. This particle shape is flake shape, but after mechanical fusion, there's no change for the particle shape, and also no change for the particle size. But pore density, capital density increased, and also cohesion reduced, better deglomerated, and better dispersion. The FPF increased from about 65 to about 80. We examined the third drug, fluting Zhou. Also, the dispersion increased from about 48 to about maybe 68. So actually, above three drugs confirm that we can improve the performance of the drug powders by mechanical fusion. But questions like, can we just conclude that we can normalize all the drug performance by coating? I think it may be too early to conclude this, because just in case some particles just look like the same, but they didn't perform the same. So actually the conclusion here is, dry coating drug particles with the proper additive, here is magnesium stearate, we can substantially improve the flow and the aerosol performance of the dry powder inhaler formulation. And we believe such improvement contributes to the modification of the surface particle interaction by the surface dry coating. And also the relevant characterization on the powder bath behaviors can provide the detailed information on the particle interaction, and this will help prediction on the formulation performance. And finally, I would like to thank my supervisor, Gavin Morton, Peter Stewart, Ian Larson, and also my colleague, also my wife, Mr. Li Qi, and also Ray Armstrong and Tim Freeman from Freeman Technology. And finally, thank you very much and appreciate your questions. Thank you.
Thank you, Mr. Zhou, for this interesting presentation, which is open for discussion. Are there any questions?
Just a question to clarify what I've read so far in the conference. You use 10%, right? They improve the improvement of your final fraction.
Yes.
80%. Is that the max theory that you use is 10%?
Actually, we try to coat with different content from 0.5 to 10%. Yeah. But finally, we found 2% from 1% to 2% will be the optimal coating content.
Yeah. Thank you.
Do you expect the yield to be a concern? Like in pharmaceutical processes, typically it's bad, so the equipment is cleaned out, and so do you anticipate that a lot of the drugs will be wasted because they're stuck in the machine when you're done?
Sorry,
with the yield. So you put the drugs in and you do mechanical, and then when you're done, how much do you actually get out? 90%, 80%? Do you expect that that will be a cost problem on scale?
Yeah, sure. Okay. Actually, we have measured the yield. Actually, for this very small lab scale system, we can get 80%, 85% to 90% of the yield. So actually, it's quite a nice result. And we believe if we use the big machine like a pilot scale or the manufacturing scale, we can get even much more yield. Because for the small system, the ratio between the data space and also the processing value will be little for the bigger scale one. So actually, we have tried the different scale. We have tried this one. We also tried the pilot scale one. We found the performance is quite good. Reproducibility is very good. We have some kind of result to prove that, and we think it's quite reasonable. Thank you.
You showed clearly that having a coating, everything is much better. But the first thing starts with the breaking up of the agglomerates. And you did not tell much about the braking forces during this mechanical treatment. Could you tell a little bit more about that?
Okay.
How they brake, which forces are involved, and why is it so efficient?
Okay. Very good questions. I think because this is quite a new technology, and not so many people has employed this area, because this mechanical fusion system was developed maybe early of the 90s or the end of the 80s in Japan. They found that this machine is working, but the question is the very good question: why it is working? What is the processing force in the processing chamber, and how they predict how they process each other, interact each other? What I said in the presentation is quite complex. So actually, we haven't had any detailed information about that. Actually, I think Professor Prefer from the New Jersey Institute of Technology, they have done some simulation and modeling on this system. But what I can say is we still need a lot of work to do that and to improve our understanding of that system. But what I show is an application in the pharmaceutical system show that this is working. Thank you.
Just in addition to this question, when you think about scale-up processes, I think the one law to build scale-up processes is to control the specific, or to have a constant specific energy input into the apparatus. And this referring to the question of the yield. When you have a constant energy input, you may have also the same yield. You will not control, you will not have a better yield when you have a real process with the same energy input. Or you will control the energy input for upscaling? Or what is the upscaling? What would see the rule for upscaling the process?
I think actually what we control, we have some ongoing project to evaluate different coating parameters on the coating quality. For example, we can control the speed of the rotation speed of the processor. We can control the processing time. But of course, this is material dependent, and we have some results show we can scale up from the lab scale 1 to the pilot scale 1, but we haven't had any evidence for the manufacturing scale 1. So I think this is very good comments, and we will explore this area. Thank you.
Do you have any idea about the influence of mixing time or processing time and energy with your mechanical fusion or your performance of the power?
Yes, this is what I said. We have some experimental results. We have some project ongoing to evaluate that. But at this stage, we show, actually, we haven't had any result on the drug powders, but we have some results for the lactose powders. We show for the lactose powders about 20 micron. We have the speed, the rotation speed of 4,000 RPM, and the process 10 minutes should be enough for a good coating. So actually, this is quite efficient and effective method because we coat only 10 minutes. And that compared to the tumbler mixing, you even tumbler mixing that maybe for 3 days, 4 days, you still cannot get the so good coating. So it's very efficient method.
We have time for one more question. Is there any more questions?
Thank you for your presentation. I'd like to ask you the particle size effect. In your case, the lactose particles and the magnesium stearate particles is very different size. If the particle size is very close, what happens in the mechanical fusion system?
Particle size.
And the coating particle size is almost same.
Okay, yeah, sure.
What happens?
Okay. I think I need to clarify about magnesium stearate. Because magnesium stearate is kind of pharmaceutical lubricant, they form this kind of layer by layer laminar structures. So when you smear the magnesium stearate on the drug particles, they will different layer will slide to each other and will be delaminated on the surface. So actually, it's not like individual particles of the magnesium stearate on the drug particles. So actually, this smear like rubber. So we form very, very thin layer, we have some rough results show that this layer can be as thin as 10 to 20 nanometer. So it's like a several, maybe one or several molecular layer on the surface. Thank you.
Okay, this concludes the discussion. Thank you once again, Mr. Zhou, for the interesting presentation. We proceed to the last presentation in this session, which is